in here, actually. You know, these pictures of nice conferences in Corsica. I'm going to try to introduce you into concepts of optoacoustic imaging as well, which are not very simple because it's opto and acoustic. So you enjoy, of course, from both worlds, but also have the troubles of both worlds. So the theory is quite complicated. So I'll try to show things on images instead of formulas. There are going to be a few formulas, but don't be too scared of this. It's going to be just 2 slides, maybe. Okay, so optoacoustic imaging is optical and acoustic, and the important part of it is optical because this is where the contrast comes from. So the contrast in optoacoustic imaging is optical. It's not ultrasonic. Therefore, we can enjoy from all these advantages of optical imaging and microscopy, so a very rich molecular and functional contrast. A lot of different contrast approaches that can be tried: particles, fluorescent proteins, cell receptor targeting, enzyme activation. So whatever is relevant for optical imaging would be also relevant to some extent in optoacoustic imaging. And of course, the costs of optoacoustic imaging are relatively low because it involves ultrasound and optics, and both are not super expensive modalities. It's also, at least the optical part is simple, it's intuitive, and optical imaging also allows you to penetrate up to several centimeters into tissues, at least in the near infrared range. So it also makes it relevant for some clinical applications. And of course, optical imaging is cool. It got a lot of Nobel Prizes, as you know, fluorescent proteins, super resolution, and so forth. So every few years, there's another Nobel Prize. I'm not sure there's going to be a Nobel Prize for optoacoustic imaging because the inventor died many years ago, but we'll see. Okay, so the main problem of optical imaging is obviously scattering, as you have seen previously. So if you try to image, for example, a living mouse brain, which is labeled with some fluorescence dye or protein, this is the kind of image you're going to get non-invasively. If you just put a camera, fluorescent filter, so completely diffuse appearance, and you cannot really discern anything in the brain itself with any kind of usable resolution. So people came up with all these sophisticated methods to clear scattering. So for example, like this is one of the recent V-disco tissue clearing approaches where a group in Munich of Ali Erturk managed to clear the whole mouse. We have it in neighboring institute. It's really scary. You can see through it completely. Some organs are stained. So yeah, but it's a dead mouse, right? So it takes about a week to clear completely. So quite invasive approach. But still, it's very useful because once you cleared it, you have a snapshot of a living organism. So for example, this is a light sheet microscopy of a cleared mouse brain. It's an Alzheimer's disease model. So we basically used an optical dye to stain the Alzheimer's disease plaques all across the brain. And we could visualize them with a resolution of a few microns in the whole brain, which is like 1 centimeter across. So SPIM or light sheet is still a very useful approach. But again, this is only applied ex vivo to cleared samples and extremely time consuming. So this is not suitable for studying living organisms, or almost not suitable, I would say. Okay, so what about living tissues? So optical imaging of living tissues is quite old. So already in 1929, Cutler was able to trans-illuminate the whole human breast. And the idea was to diagnose different types of lesions. So he saw those kind of appearances of, for example, malignant tumor versus just mastitis versus the normal breast. Of course, it may work in some cases where you know that you can definitely know that this is cancer, but in most cases this is not very specific, right? So The resolution is very bad because the light goes through many centimeters of tissue, so you don't really know where those structures come from, how deep they are, and especially if you start using fluorescence, it even becomes worse. So obviously, a big problem in optical imaging in general is photon scattering. So if you're using optical microscopies here, so up to about penetration of about 1 millimeter, so confocal, multiphoton, OCT, they all go up to about 1 millimeter in the tissue, maybe 2 millimeters, and the resolution is very high, so you can get below a micrometer even. Once you try to use near-infrared light and go deeper, you immediately start losing the resolution. So basically, techniques like diffusion optical tomography or fluorescence molecular tomography, you can penetrate several centimeters, even in a human brain, like in the case of near-infrared spectroscopy, but the resolution is very poor, right? So you're talking about several millimeters or even a centimeter of resolution, so you have just a few pixels in your image, right? So this is kind of a physical law of diffusion, and it's very difficult to overcome it. So basically, you have a gap, right? So if you want to go deeper, you have to sacrifice resolution completely. This is where actually optoacoustic imaging could really help, as I'll explain later. So this spatial scale is important, but what is also important in imaging is temporal scales, right? So if it takes you a few hours to acquire an image, or even a few minutes, there's not too many things you can do with this kind of modality if you want to look at biological dynamics, right? So if you just look at development or just agent uptake that may take a few hours, it's fine. You can acquire an image for a few minutes, it's no problem. But if you start looking at things like kinetics of contrast agents, or heartbeat, or flow of cells, or even neural firing, then you need a temporal resolution of below a second or below a millisecond even, right? And all these temporal scales is very difficult to breach with one single imaging modality. So you would use maybe PET here, ultrasound here, two-photon microscopy here, and it's all very different contrast, right? So if you try to combine those images, it becomes not very valuable in some cases, and difficult to register the scales and so forth. So it would be ideal also to have a modality that can breach not only the spatial scales, but also temporal scales. So optoacoustic imaging may help, and it can solve many problems in this sense, because the way it works, it uses light for interrogating the tissue. So you shine very short pulses of light, so about a few nanoseconds usually. This pulse gets absorbed, so photons go everywhere. It's not necessarily has to be focused light, it could be also unfocused light. When the photons gets absorbed, there is instantaneous heating, right? So there's a lot of photons going in. There's a heating of a fraction of Kelvin, not very major heating. And then there is thermal expansion because of the heating. And then pulse stops within a few nanoseconds, right? And then tissue shrinks back. So there's a tiny vibration everywhere. And these are basically how this is how basically the pressure waves are generated. Then they propagate in the tissue, and we detect them with ultrasound sensor, which is typically placed on the surface of the tissue next to the skin, or where you have a good coupling, acoustic coupling. So this is the basic principle. And just a few slides of history. It's very interesting. The principle of optoacoustic imaging was invented in 1880 by Alexander Graham Bell and his assistant Charles Tunter, and they called it the photophone. And the way they try to use it is actually to transmit speech over distance using this phenomenon. So the idea was to use sunlight and modulate the sunlight with a mouthpiece. So basically the intensity of the light was modulated when someone was speaking. this was transmitted to the other side where there was a selenium cell receiver. So it's an absorbing material that basically generates the signal based on the modulated speech of the transmitter here. So they managed to transmit speech over a distance of about 200 meters in 1880 in Washington, D.C. And of course, this was not very useful idea, because in a few years later, Marconi was transmitting speech over Atlantic Ocean using radio frequency waves, right? So this only works on the line of sight. But nevertheless, this is a first example actually of wireless telephony or optical communication, right? So it's pretty interesting. So it took many years for it to evolve, but maybe before I switch to the next development, so this is a letter actually from Alexander Graham Bell that he wrote to his father in 1880. He was very excited about his discovery, and here he says, "I have heard articulate speech produced by sunlight. I have heard a ray of the sun laugh and cough and sing." So, because the clouds were passing, blocking the sunlight, so he heard it with the telephone. Right. So then, fast forward to the 20th century. So 1938. A Russian scientist in Leningrad used for the first time optoacoustic phenomenon for spectroscopic detection of gases. So he was able to measure very small at the time carbon dioxide concentration in nitrogen gas. So it was a spectroscopic application. So not communication, not imaging, but spectroscopic application in very sensitive gas sensing. Next thing that happened was the invention of the pulsed laser in 1960, which was awarded the Nobel Prize. Actually, the first laser that was invented was a pulsed laser. And this is kind of the laser that we usually use in optoacoustic imaging. So these three gentlemen were awarded the prize, and a lot of controversy. I'm not sure you know about this history, as many times with Nobel Prizes. So those two guys, Theodore Maiman and also Gordon Gould, thought that they deserve it more than those three. So yeah, it's a very interesting story as well. But nevertheless, for the purpose of optoacoustic imaging, this is a major development because you cannot really do it efficiently with CW light. You need pulsed light. And then another 20, 30 years, so we're already in the 70s, 80s. So first ideas of using it for biological sensing, not even imaging. So Alan Rosenzweig proposed to use it for spectroscopy of blood, which makes sense. First experiment with a living rabbit. So basically they used this very powerful laser. They shine it through the eye of a living rabbit. It's terrible. I mean, when I was reading this paper, definitely not something you can do these days. But nevertheless, 1964, first signals of elastic waves generated by a laser. This paper of Amar. Okay, so still no imaging, right? So you were probably wondering when the imaging came. So it's this century. So we are 20 years ago, 2001, 2003, first in vivo images from human breast here. Not super impressive. I don't even know what you see in here. It's probably just the skin, or no idea. I was asking Oraevsky actually, what is it that he saw here, but he couldn't tell me either. And then 2003, actually something more impressive, because you have the resolution here at least, and see some vessels in the mouse brain. It was done with craniotomy, I believe, so the skull was removed, which we don't have to do usually in optoacoustic imaging. But nevertheless, this was a kind of a breakthrough in terms of in vivo imaging. And they even showed how you can modulate the brain activity and show some hemodynamic changes in the brain. Yeah, so the problem that this image took, like I read it, it's like 45 minutes. So I was wondering also, like how you see hemodynamic changes over 45 minutes if just an image acquisition takes so long. So one couldn't answer me either. But nevertheless, if you look at the system, it's a mouse sitting in a water bath. Here is one transducer rotating around the head. The light comes from the top. Yeah, so you would call the setup a scuba diving mouse because there is a mouthpiece here. So the mouse is breathing through the tube. And again, those images took about 45 minutes because you had to go with the transducer around the head, stop at every position, and this way you acquire an image. So it's a tomographic reconstruction, actually. Okay, but this is like 2003, so very primitive, right? So like we are already this century. So why would you do it this way? And don't be surprised because this is exactly how ultrasound was done in the beginning. So if you look at this guy here, sitting in a water bath, you know, it's just, I think it's like I don't know, it was Times magazine or like the first cover image like this, you know, sound wave portrait in the flesh. It's amazing. So Douglas Harry in the University of Colorado actually imaged a human leg. This is the first ultrasound image, 1954. Again, took, I think, more than half an hour to have one cross-section of a leg. So, like, it's actually similar to what was going on with ultrasound imaging 70 years ago. So, just to look at the time perspective. So, this is the way optoacoustic imaging was done in the beginning. Okay, so but I'll stop with history now. If you're really interested in this, we wrote a paper with Shriyan Manohar a few years ago here, where we tracked all the developments from the invention of this phenomenon through the years. So if you're interested, take a look. Okay, now let's get to how optoacoustic imaging is actually done these days. So for this, obviously, you would not use a single element detector. Usually, if you want to do fast imaging, you would use a transducer array. So for example, here it's a linear array, which is, I'll talk about it later. It's not a very good idea to be used for optoacoustic imaging. And then you need some light source. You shine it on the tissue. You detect the responses, the ultrasound responses with a transducer array. And so light goes in, sound goes out. So again, a takeaway message is that the imaging contrast is optical, but you are not affected by light scattering because you detect ultrasound, right? So your resolution is established by the diffraction of the ultrasound waves. So you can have very high resolution in deep tissues. So not millimeters or centimeters, but you can have a resolution of tens of hundreds of microns at a depth of few millimeters or centimeters even, with optical contrast. Okay, so that's what it is. Now the contrast itself could be spectroscopic. So if you use different wavelengths, you can interrogate different chromophores or molecules in the tissue. So the major absorber in mammalian tissues is of course blood. It absorbs a lot, especially in the visible range. And this is what also limits the penetration of imaging. If you use visible wavelength, the light just doesn't go through. It gets absorbed very quickly because of blood. If you move into near-infrared, it becomes easier to do deep tissue imaging. And here you have still the blood absorption, so you can do spectroscopy of oxygenation for oxygenation sensing, for example. And also sense some other molecules like collagen, elastin, water, fat, melanin. And these are all useful for disease diagnosis in the near-infrared 1 and also near-infrared 2 window, which is longer wavelength beyond 1000 nanometers. Now, let's take a look at a very simple optoacoustic imaging experiment. We call it 1D imaging problem. So you have, for example, this is a breast, and there's a tumor somewhere. okay? And the tumor has different color, so it will absorb more light than the surrounding tissue. So let's say this is a fatty tissue and this is a tumor, just as an example, okay? So let's do a simple experiment. So we shine laser from that side and we detect it with the ultrasound detector on the other side, and here is water around the breast, just to let the ultrasound wave propagate, okay? So in the beginning, in a few nanoseconds, light goes in, and on acoustic scale, this is nothing. It's very short, right? So no acoustic propagation is happening within a few nanoseconds. And then light gets everywhere within picoseconds even, right? So it's very fast. And then the whole tissue absorbs light, and then ultrasound waves start being generated. And of course, if you sense with the ultrasound here, with the transducer here, so the first ultrasound signal is going to come from the surface of the tissue here, right? And this is what we see in the detected signal. So in the beginning, it takes time for the ultrasound to propagate through water. And then you start seeing the signal going up a little bit. And then comes a big signal. And this one comes from the tumor. Because the tumor absorbed a lot of light, it generated a lot of sound, and it took a bit longer to propagate. So the surface signal comes first, then the tumor signal. And afterwards, signals from everywhere in the breast will arrive at the transducer, and you will see more signal coming into the transducer, because all these signals sum up on an arc, depending on the distance, right? So an important thing to see here in the signal is the duration of the signal that you detect from the tumor is proportional to the size of the tumor. So the optoacoustic signal duration is proportional to the size. Why? Because sound is generated in an object everywhere. So it's very intuitive to understand that basically the duration and time of the signal will be proportional to the size of the object, right? Okay, so this is 1D imaging problem. Obviously, this is not how imaging is done, because 1D is not imaging. So optoacoustic imaging is done in 2D or 3D in different ways. So one popular way of doing optoacoustic imaging is microscopy, where you have a single detector, ultrasound detector, and you focus light on the tissue surface. So this is similar to optical microscopy, because light is focused now. And then you scan the beam on the surface, sometimes together with the transducer. And this is the way that you form in an image. So point by point, right? Scanning in X and Y. This is not very deep. So of course you cannot focus light very deep in the tissue. So it would only work up to a depth of 1 millimeter. It's quite slow because you have to scan. So if you want to go deeper, you use unfocused light. And then you focus the ultrasound waves with a spherically focused detector. So this is called mesoscopy. Mesoscopy because it's not optical microscopy anymore. It's a mesoscopic regime where light beam is unfocused. And then you form images based on ultrasound focusing, not optical focusing. Okay, so the resolution goes down, so you're not few microns anymore. You're a few tens of microns if you use high-frequency ultrasound. The depth is better, so you can usually use it for a few millimeters of depth already. But acquisition is still slow, right? You have to scan. Now comes the third case of tomography, and here there's no scanning because you detect tomographically all the ultrasound waves around the object with a lot of detectors. So the resolution is again acoustic. It's not optical in this case. You form image with tomographic reconstructions, so this is very fast. So you can capture all the 2D or 3D information within milliseconds. So this could enable real-time imaging in 2D and also in 3D. So one single laser pulse, and you can form a 3D image. You don't need to do beamforming, by the way. So the difference from ultrasound is that in ultrasound you would need to steer the beam, right, to form an image. Here it's one pulse is enough, and you have a 3D image. So it could be very fast. Now, let's see some examples. So, for example, in scanning optical resolution microscopy, this is kind of images that you get usually. Beautiful images. Why? Because main contrast of optoacoustics is blood. So whatever has blood, like blood vessels, would have a lot of contrast. And since it's microscopy, the resolution is also very high. So a mouse here, for example, is very thin, so you don't need to, you don't have any diffusion or scattering. So you can reconstruct this kind of image over a field of view of a centimeter. So no problem. And the resolution is a few microns. If you use several wavelengths, again, you can do spectroscopy, like in pulse oximetry, for example. So you use 2, 3, or 4 wavelengths, and in this way you can resolve the SO2 in the individual capillaries. And even if you're fast enough, you can see some changes in the oxygenation of blood in those vessels as in response to, for example, stimulus. So this is in the mouse brain, and here you see the signal, the colors changing, which means the SO2 in the vessels is changing. And all of that can be done label-free, so it's pretty cool. So no contrast agent needed because your contrast is blood. Now let's see a few more examples of beautiful images. So this is a study we've done with a wound model. So we induce a wound in the mouse skin and track it over time. So 2 weeks of time and see how it heals, basically. So this is the pre-wounding image of the microvasculature in the skin. Here you see the wound is created. After 5 days, it starts the angiogenesis processes around the wound. Here are little capillary forming to bring oxygen to the wound to start healing. You can track it longitudinally over time. So day 5, then day 10, day 13, and here you see the wound is already closed. So we are now thinking of using it for developing new wound healing drugs. Another example is mouse brain and the skull. So in this study, we actually started off with trying to look how radiation treatments affect brain vasculature. So the hypothesis was that some microvasculature may be damaged by the radiation. So we were looking hard into the brain vasculature and increased the radiation, increased, and the brain vasculature was not damaged. So we thought we stopped the project. And then we discovered that actually the skull vasculature is completely destroyed, not the brain vasculature, even at very low radiation doses. This was an interesting discovery. And this was all done with optoacoustic microscopy because skull of the mouse is very shallow. So we could effectively focus light up to the cortical areas. And here you see untreated mouse. So the vasculature in the skull is shown in blue. So it's unaffected. And this is a radiated mouse with a normal safe dose, which is considered in radiation treatments. So half of the brain, so one hemisphere was radiated, and you see all the skull vasculature is gone. So only brain vasculature appears underneath here in red. Okay, and it actually developed further, and it became worse after 11 days. So the vasculature was completely gone in the skull. If you want to do something deeper, so for example, human imaging with this method, optical resolution microscopy will not work because you cannot focus light through a human skin. And in this case, you can use what I mentioned, mesoscopy. So it's an example of study done with what is called raster scan optoacoustic mesoscopy. Here the light is not focused anymore. There is still one single transducer which is being scanned on the tissue surface. And this takes you a bit deeper, so a few millimeters of penetration through the skin. So you can nicely see all the skin layers non-invasively. So not really possible with other optical imaging methods like OCT. It doesn't go well through a human skin. Here you see an example of psoriatic patients. So the vasculature is very different in psoriatic skin versus healthy skin. And they also showed that this basically imaging method can be used for non-invasive diagnosis of psoriasis, which is usually done with some histology or some invasive means. So the indices of the biomarkers of disease were aligned pretty well with histological evaluations. Okay, now the difficult stuff. So this was all about nice images. So as I mentioned, if you want to go deeper, you cannot use microscopy or scanning mesoscopy because it's still very shallow. And then you have to think how you actually do tomographic reconstruction. And on top of it comes also different effects that I'm going to talk in a while. So optoacoustic imaging is optics and ultrasound. So if you look at the whole pipeline of imaging, so what happens during the generation of optoacoustic signal, it's a lot of different things. So first thing that happens is that light interacts with different chromophores, 1, 2, 3, 4, for example, oxy-deoxy blood. And all those molecules, they generate signal, right? So it all adds up to what is called the optical absorption coefficient, right? And then comes the light fluence as well, because your signal also depends on how strong is the light in every particular voxel in your in the object, right? So if you combine those two, this is what generates the heat. So it depends on optical absorption coefficient and light fluence in this point, right? And then there is the propagation of the ultrasound wave as a result of heat generation, and this is what you detect, the pressure profile on the surface of the tissue. So there's a lot of optical, acoustic, mechanical processes, physical processes happening on the way. And now if you detect the pressure, you obviously want to go all the way back and see what is the distribution of different chromophores in the tissue, right? This is the goal of imaging. So how do you go all the way back? So you need to take it step by step, right? So you detected pressure, you have to transform it into a map of absorbed energy, right? So what was the heat generated or the energy absorbed, right? Then you have to uncouple the light fluence because this is not related to the object. This is something external, right? So you have to take it out. Like in MRI, you have to cancel the field inhomogeneity of the B field or so forth. So it's same here. You have to take it out from the equation and get to the map of optical absorption coefficient. And this is actually, this consists of contributions of many chromophores. So you need to unmix it now, right? And split it into different chromophores. So this is the last step of optoacoustic imaging. So to build different maps of chromophore concentration, different concentration of different chromophores in the tissue, right? So it's very extensive process, right? And every step involves a lot of equations. I'm not going to show all of them, but just one of them. So let's talk about the first step. So how we take the detected pressure variations and build a map of absorbed energy. So this step is called the acoustic inversion in optoacoustic imaging. And you need an equation to do this. So equation is the ultrasound wave propagation in the tissue, right? And you have a source on the right side, right? And the source is basically how much energy was absorbed, right? So you have a source term on the right side of the equation. The left side is the ultrasound wave propagation in 3D, for example, yeah. Okay, so you solve this equation and you end up with a well-known equation of the detected pressure. That's basically a Poisson integral, right? So you have to integrate, for every distance from the detector, you have to integrate all the sound that was generated on the arc at equidistance from the detector, right? This is what the equation says. So certain distance from the detector, and then you have to do it for all the distances the same, right? So if you want to build a waveform in time, you need to use this equation. And this equation is called the forward model of optoacoustic imaging. Okay, so this tells you what is the sound which is generated by the detector, but what you're interested in is actually those sources, right? So you are looking for the sources that generated this ultrasound wave. So you need to invert the forward model, right? So this can be done analytically. So you take this Poisson integral, do some mathematical physics developments, approximations, you end up with an exact formula, which is called a back projection formula. It's quite similar to X-ray CT. So in X-ray CT, you have a linear propagation of waves. You have detector, you have the source, and there you have a linear radon transform, right? Because X-rays propagate on straight lines, ultrasound propagates as spherical waves, right? So it's quite similar. And here in this equation, you have those detected pressure variations on the right side. You need to do some integration, and you end up with the reconstructed source map of the optical absorption in the tissue. So this is simple because you have an analytical formula. But this is an approximated formula, so nowadays what we usually do is not analytical inversion because it's not always accurate. I'm going to show you now an example. So we rely on what is called semi-analytical model-based inversion. So we take the forward model, and instead of building an analytical inversion formula, we just discretize it on a mesh and then invert the exact matrix which represents this forward model. Okay, so this can be done with Moore-Penrose pseudo-inverse or some other methods in MATLAB. Yeah, and this is the result. So these images are taken from a zebrafish, and you can compare the model-based, which is an exact inversion, to back projection. And this is approximated. Now you would say that probably this image is better than this one, right? Because it's blurred. But the problem of this image is that it's a high frequency image and there are even negative values in the image. So if you look up the values here in the middle, they're negative. And what is the meaning of negative absorption, optical absorption? There's no meaning to it. And here all the values are at least positive. So that's already good news. Now if you want a high frequency content, of course you can high pass filter this image and you can end up with this image. So this image contains actually all the frequencies, whereas this one basically discarded all the low frequencies, which is very bad because it ended up with inaccurate image with artifacts and negative values. Okay, so just to show you how important it is, well, I'm not sure where. Actually, I switched the slides somehow. So to show you how important it is, here's an example of imaging glioblastoma in a mouse brain. Okay, so we did MRI, we did optoacoustic imaging. Now you can see the comparison. This is back projection reconstruction. Now, and this is model-based. Images look quite similar, but if you look up here, the values in the center, they're all negative. Now, if you want to do more than this, more than just looking at the image, you want to see the tumor, right? So you do some spectroscopic inversion to end up with oxygenation of blood in the brain, and this is what you get. So all this black space is actually negative values that you cannot invert spectroscopically. So you end up with completely useless image. Now model-based, it's all positive values. You can invert, you can do spectroscopic inversion, and you end up with this image. And here you see the tumor area. It's more oxygenated than surrounding areas. And it actually can be validated with the location of the glioblastoma in the MRI image. Okay, so if you want to track hemodynamic changes after administration of, for example, vascular disruptive agent, if you use back projection formula, you cannot do it. Okay, so here with the model-based reconstruction, we were able to track it over time very nicely, and we saw how the vascular disruption agent, how the brain responds to the vascular disruption agent after 1 hour, 4 hours, 6 hours. Okay, now back to a bit of theoretical part. So besides the acoustic inversion, we also have the optical inversion problem, which is spectroscopic inversion, right? So if you look at what you do in this case, so you need multiple laser wavelengths to do spectroscopy, right? So what you do in what is called multispectral optoacoustic tomography, you shine light different pulses at different wavelengths. For each wavelength, you do the acoustic inversion. So you detected the signals at multiple locations around the object. You do acoustic inversion. You build images separately for every wavelength. And the last step is spectral unmixing. So you use the extinction coefficient spectra of different chromophores, so the blood, the melanin, some contrast agent that you injected into the tissue, and so forth, and you end up with those images. And those images represent the concentration map of different chromophores in the tissue. So hemoglobin, deoxygenated hemoglobin, oxygenated hemoglobin, infrared dye, and so forth. So this is the end goal of the multispectral optoacoustic tomography imaging. And now this technology is also commercial. It's commercial by our spin-off in Munich. It won some prizes as well. Just to show you a cartoon of the system, it looks like this. So if you zoom into the scanner head, there is an ultrasound transducer, a lot of elements around the mouse here behind the black surface. There is some light going into the mouse here in red around the circumference, and every pulse of light generates those ultrasound responses shown here in blue. This particular configuration was built to do cross-sectional imaging in real time, so two-dimensional imaging. But if you want to build a three-dimensional image with a scanner, you can advance the mouse through the scanner and build the images of different slices one by one. So here the mouse starts moving, and you can do 3D imaging as well. So this was developed around 12 years ago, 13 years ago, and we called it multispectral optoacoustic tomography, or MSOT. I'm not going to go too much into applications that can be done with this kind of technology, just to show you a few examples of functional, metabolic, and molecular imaging. Because again, the contrast is optical, so we can do all the nice things that optics enables. First and foremost is probably sensing blood, right? So oxygenation of blood, it's very important biomarker of many diseases. One of them is cancer. So you can sense cancer hypoxia, for example, with very high resolution, non-invasively, and also over time. So really look at oxygen gradients across the tumor core, the normoxic and the hypoxic area, and so forth. The imaging is very fast, so it's real time. So you can also look at, for example, kidney metabolism, so perfusion of contrast agents through healthy kidney versus diseased kidney. This is what was done in this particular study. Here is an example of molecular imaging study where a group in Louisville in the US were interested in developing new targeted liposomes for pancreatic cancer sensing. And again, MSOT can be done non-invasively, and you can look up the uptake of the agent in the tumor versus unspecific clearance through the liver and kidney. And again, all of it in vivo and non-invasively. Yeah, that slide was previously. So now let's do a quiz to wake you up from the first and the heavy part of my lecture. So who wanna answer the first question? So both imaging contrast and spatial resolution and optoacoustic imaging can be determined optically. Is it true? Right, but it says can. So answer is yes, right? So there's optical resolution where you focus light, so the resolution is optical in this case. So that's right. Next question. Pulsed laser are used for optoacoustic signal generation. Yes. Good. Third one. So optoacoustic imaging is slower than optical imaging because acoustic wave propagates slower than light waves. You know everything. Someone else, is it true? No. True? Mm. Well, yeah, okay. So, come on. I was saying all the time it's so fast and so, you know. But right, but actually, well, I'm not sure if it's always faster or not. But what it says actually is slower than optical because acoustic wave propagates slower than light waves. Well, even if it's slower, it wouldn't be because the propagation speed, because the speed of imaging is not determined by how fast the waves propagate anyway very fast. So acoustic waves propagate in like in few microseconds, optical waves in few picoseconds, but it doesn't change the frame rate of the imaging. So yeah, so that's wrong. Optoacoustic imaging is not a label-free imaging method. It is label-free, right? So it's wrong. Last one. So visible wavelengths are less preferred for optoacoustic imaging due to the limited imaging depth in living tissues. Correct, right? So visible light is not a good idea for in vivo imaging, for deep tissue imaging, I would say. Okay, so this is right. Good. So now hopefully you woke up. So yeah. Right. Well, it depends on the method itself. So in optical imaging, you also have tomographic or scanning microscopy, and same here. So it would be the same because the amount of data that you get would be also similar, right? So with two-photon microscope, you would get gigabytes of data in a few seconds as well, and here it's the same case. So the reconstruction itself, I'm not sure this is a factor. But in terms of speed, I'm not sure you can do optical imaging because, as I mentioned previously, in optoacoustic imaging, one pulse of light is enough to reconstruct a three-dimensional image. I don't know how would you do it in optical imaging. I mean, I'm not aware of such a modality that can acquire all the 3D data at once. So probably it would always be slower, actually, than optoacoustic imaging. But in any case, I mean, the question is not about the speed itself, but because the speed of propagation of waves, which has no direct effect on the imaging rate, I would say. Yeah. Okay, good. So next part is like more advanced stuff, I would say. A few years ago, well, it's actually 10 years ago already, we started developing a very fast volumetric imaging technology. So really volumetric multispectral MSOT. And the idea was to use this big spherical matrix arrays that we put around the object, so basically to mimic full tomographic acquisition. Of course, it's not full because we cannot surround completely the object with sensors, but nevertheless, we get up to coverages of 120 or 150 degrees around the object. It has a lot of elements, so for every laser pulse, we would acquire 512 channels, for example. So, and we can run it at the pulse repetition rate of the laser, which is quite limiting. So currently we work with lasers of like 100 hertz lasers or a few hundred hertz. But nevertheless, you get a lot of data. So like 100 times per second, you get 512 channels. So fast speed acquisition of all the channels at, I don't know, 100 megasample frame rate. So it's very a lot of data generated within seconds. And this technology can enable 100 hertz volumetric frame rate, limited by the laser again. Spatial resolution depends on the bandwidth of the ultrasound, typically between 35 to 200 micron. And penetration is limited by light penetration of near-infrared light up to several centimeters. So just to show you an example of what this technology can do, here you see it's operated in a handheld mode. So this is a spherical array. You can hold it in your hand. There's a membrane here in the front. You can attach it to the skin and start moving the scanner, the probe on the skin surface. Here you see three-dimensional images rendered actually in real time at I think 50 volumes per second actually. So we use GPU to invert the data very fast, so you can actually see it on the screen in real time. And this is a three-dimensional image. So here you see some vasculature in the breast. This is a healthy volunteer, and these are three projections from three directions. So top projection and two side projections. So basically all of it, all the volumes rendered in real time. If you move the probe, you can see everything changing at 50 frames per second. So obviously this is useful for many applications. So in preclinical imaging, brain imaging is something where you do need some speed, right? So if you study brain activity, for example, here you see a study we have done with epileptic seizures. So we induce an epileptic seizure in a mouse brain, and you need acquisition on a sub-second scale to track the propagation of the epileptic seizure. So what happens, we capture the start of the seizure with EEG, and then we start the three-dimensional recording of oxy and deoxyhemoglobin distribution across the whole brain. And then you can reconstruct three-dimensional maps of the changes of oxy and deoxyhemoglobin, and you can nicely see where the seizure originates. It's in the cortex. And then after a few seconds, it moves into thalamus. There is some activity there, and then closes a loop. So you can see it on temporal scale. So if you do the time to peak analysis in different brain areas, you can nicely see that the seizure originates in the cortex, propagates into thalamus, and closes the so-called thalamocortical loop into the cortex again. Another example how you can use it for brain imaging is non-invasive detection of Alzheimer plaques. For this, you would need some labeling because what you want to see is the plaques, and they're not well contrasting in intrinsic optoacoustic imaging. So we used a near-infrared dye, which can be targeted to, so it's oxazine derivative of a beta targeted probe. So actually it's 650 nanometer peak absorption. And then we do longitudinal imaging over a month. And here you see that at 14 months, in 14-month-old Alzheimer mouse, the plaque load is lower than at 15 months of age. We haven't done it to try to detect the sensitivity limit, like how early we can detect Alzheimer, but probably this would be the next step to see really at what age we can detect the plaques at the earliest possible time point. Again, this is optical imaging, right? So if you compare it to a fluorescence, for example, so this is what you get from that mouse. So really just some diffuse pattern of fluorescence, because there is so much diffusion going on in the deep tissue. And here you can resolve the plaques with optoacoustics at 100, 150 micron resolution. Obviously, speed is becoming important when you look at cardiac imaging. So heart is beating very fast. So if you want to study something in the heart, you really have to become very fast. And this is possible because with 50 or 100 volume per second frame rate, it's enough to capture the full cardiac cycle without any gating. So if you inject a contrast agent, for example, you would see, like indocyanin green, you would see how it perfuses the heart chambers in real time and goes from one ventricle to the other. You can start characterizing some parameters like pulmonary transit time, for example, in infarcted heart versus healthy heart, some second, third harmonics of the heartbeat, and so forth. So speed is not is also important in the brain if you want to study not just hemodynamic changes but actual neural activity. You have to work with very high frame rate imaging, right? So calcium waves are generated and propagated at a sub-second scale. So with optoacoustic imaging, we used the GCAMP, so genetically encoded calcium indicators, which are commonly used in two-photon microscopy studies, for example, of brain activity. And they're good enough to be sensed with optoacoustic imaging. So as you can see here, this is a wide field fluorescence imaging of the brain. You see some calcium waves. And the same you can do with optoacoustics volumetrically. So it's not just one projection of the activity, but actually 3D resolved activity in the whole cortex, not brain. Because if you it's not the whole brain because it's a visible light indicator. So the peak absorption is at 488 nanometers. So it's a visible light, doesn't go very deep. And now we are trying to move it into near infrared so we can do the same thing in the whole mouse brain. And this is, by the way, done non-invasively. So skull is intact, skin is intact. So really a good approach for studying the brain. Now, this is already fast, right? So it's like 3D imaging at 100 frames per second, but not fast enough for several things. So for example, what if you want to study some neural activity in a freely behaving animal, like zebrafish? So here, if you walk with 100 frames per second, by the time you acquire the next frame, the fish already moved. So it's not very useful. So you need to speed it up. How much you need to speed it up? Probably at least 10 times, right? So you need to go on sub-millisecond scale and still keep the 3D because it moves in 3D volume, right? So this is what we've done in this paper, where we implemented an ultra-fast acquisition with a compressed sensing approach. So instead of acquiring all the channels at several thousand times per second, because this would be too much data. It would be like, I don't know, tens of gigabit per second flowing through the data acquisition system, so we could not implement it this way. So we do compressed sensing by just sensing with few elements for every pulse, and for the next pulse we sense with another subset of elements. So this is also done in other imaging modalities this way. And now the data flow is lower, but the question is the image quality is degraded, right? Because you don't acquire all the tomographic information. So if you just do it this way, and just speed it up, you cannot see anything, right? So if you acquire with 32 channels at a time, this is how the image is going to look like. So completely destroyed, you cannot recognize where is the brain and so forth. So we implemented what is called a total variation-based reconstruction approach in a combined space and time domain. So we basically do a rolling acquisition with a random subset of elements, and after a few frames, you can actually catch up with the frame rate and have the same image quality that you had originally with all the channels, but with a subset of channels and 1.6 kilohertz frame rate, using compressed sensing and sparsity-based reconstruction. So that's good for a freely behaving organism, but where else it's important? So again, going back to the heart is also very fast. So if you just see perfusion of contrast agent in the heart, that's fine. You can have 100 volumes per second frame rate, but what if you want to look, for example, at mechanical wave propagation in the heart wall itself? So the heart moves very fast, right? So it's like zebrafish swimming. If you have 100 frames per second rate, then for every frame, the position of the heart wall is completely different. So you cannot track any wave in it anymore. So you again have to speed it up to kilohertz volumetric frame rate. And this is what we have done here using the approach that I've shown previously. It's an isolated heart. And the acquisition rate is 1.6 kilohertz. And at this rate, we could nicely map the phase of the heart, of the mechanical wave component in the heart wall. So this is the phase velocity vector. So we could say where the heart wall is moving in 3D and so forth. And now, why is it important? Because in cardiac imaging, for example, if you have arrhythmia, the mechanical wave propagates completely differently from a healthy heart, right? So this is a way to diagnose cardiac diseases. But you have to be very fast, right? So with 1.6 kilohertz, with this phase mapping, we were able to see those tiny phase singularities that correspond to spiral wave reentry during cardiac arrhythmia. So we induce the arrhythmic behavior in the heart using some electrodes and stimulation, and then it becomes it starts beating irregularly with some arrhythmic events, and they are characterized by this asymmetric entry of the waves, so these spiral waves at a certain point in the heart, and we were able to detect them using this approach. Okay, now if you were noticing what is still limiting, so the array geometry enables you to capture one organ at a time in a mouse. So the field of view is about 1 cubic centimeter. This is what you can do in real time. What if you want to image the whole mouse, for example? So the way to do it, you would move the spherical array detector along the mouse and acquire the whole body images in this way, right? So this is a spherical array. You can do real-time imaging of a heart, for example, and at the same time move it along the mouse, and in a few minutes you get this whole body image of the mouse, right? So it kind of bridges the spatial and temporal scales, right? So you're not only able to do real-time imaging of a single organ, but you can also capture the whole body image with the same type of contrast, right? So this addresses, at least partially, the spatial-temporal mismatch between the different modalities. Now we made it now even faster, so we do what it's called a single sweep acquisition. So with just a translational motion that takes about 1.8 seconds, we can capture this image using this kind of multi-beam illumination around the mouse. So basically you can image the whole body of a mouse every 1.8 seconds. And this allows you already to look at kinetics of contrast agents. So not only biodistribution, but really seeing how particles or contrast agents, they flush the vessels, how they propagate through the different organs in a spatially and temporally resolved way. Okay, maybe a few words about multimodal imaging, because obviously, yeah, so probably you have an impression that optoacoustic imaging is the best. It's not. That's why you have to do multimodal imaging. I'll explain later why it's not the best. There are a lot of challenges. These are just excerpts from the best results, right? So as usual, there are many problems. So multimodal imaging is important. And the problems in optoacoustic imaging have to do with sensitivity, with depth, with quantification, like a lot of issues. So some of them could be solved with another modality added on top. And a natural multimodal approach would be to use fluorescence imaging together with optoacoustic imaging. Why? Because you have a light source, right? So if you just put a fluorescent filter, it would already show you some fluorescence imaging together with optoacoustic imaging. But it's not easy to implement. So for example, if you use this kind of big spherical array, the whole field of view is blocked. So you cannot come with a camera anymore from anywhere. So we implemented some fiberscopic insert into the array. So it goes through, it has like 100,000 individual single mode fibers. So something that you would usually do with endoscopy, right? So you have a lot of fibers to do endoscopy, clinical endoscopy. It's done in a similar way. So basically, here we have a tiny, it's about 5 millimeter wide borescope that goes through the center of the spherical array and comes on the other side. And you can capture the fluorescence responses from the tissue surface. And in this way, you can, for example, do combined fluorescence, here shown in green, and optoacoustic imaging of the tumor, for example. So you inject the contrast agent in the sign in green. You can capture the fluorescence response from ICG and optoacoustic response from blood vessels, and so forth. And same in the brain. This is the optoacoustic image of the brain. This is fluorescence image of the brain, captured at the same time. Another fascinating, really interesting combination is MRI. So we managed to insert a spherical array into the MRI bore and make it magnetically compatible. And in this way, you have now two modalities that can do functional brain imaging, right? So you can do bold fMRI, and you can do optoacoustic imaging that would give you, again, the whole mouse brain, oxy and deoxyhemoglobin separated. You know, so these are differential readings. Bold is just one reading, right? But MRI is also important because it gives you the nice anatomy of the brain, right? So they're really complementary. So MRI is good for anatomy. Optoacoustic is good for functional readings. And then you can also co-validate the two, right? So if you you can validate the bold signal, basically, right, with another modality that reads more or less the same thing, but actually differentially, right? So this is what you see here. So the bold signal is shown here in magenta from the MRI, and the other four are coming from optoacoustic. So deoxyhemoglobin, oxyhemoglobin, deoxyhemoglobin, total hemoglobin, and also SO2, right? So it's more readings with optoacoustics. Now we looked at those curves and like, so what exactly bold is representing here? So I'm not sure if it actually matches any of those curves. Well, if any, then it would match rather the total hemoglobin and not the deoxyhemoglobin, which is here the yellow. So it's actually the common understanding in the bold fMRI is that the signal represents deoxyhemoglobin, but that's not what we saw in those traces. Okay, now ultrasound, of course, it's another interesting combination because you have the transducer array, so you would think I can get ultrasound for free, right? But the way ultrasound is done is different, right? So if you just use linear array ultrasound, you add some fiber on next to it, and this is the image you get. So in gray, you see the nice ultrasound image. Here, I think it's a mouse image with linear array. But optoacoustic signals look like some speckle noise, right? So this is in color, shows some SO2. And that's not what I've previously shown you, you know, these beautiful images of the whole mouse or vasculature. So what happened? I mean, why can't you get the same here, like at least see some vessels, right? So the problem is this tomographic coverage. So linear array, if you look at the and the field of view, you effectively have only 40 degrees around with the linear array around the image zone, right? And that's very poor tomographic coverage. So to do effectively optoacoustic imaging, together with ultrasound imaging, you need to do something else. So you cannot use linear arrays. You need some tomographic coverage. So ideally around the whole field of view, or at least more than 60 degrees, 130 degrees, something like that. And here you would see that for ultrasound, the angular coverage is not that important. You still see a lot of things even with linear array. But for optoacoustic, it's critical. So the 60-degree optoacoustic image of the mouse cross-section, you see nothing, not even the skin surface clearly. And as you go to 270 degrees coverage, the image quality becomes much, much better. So we implemented it in this way, and we did both ultrasound compounding with a lot of elements and optoacoustic imaging, and this proved to be a better way of doing hybrid optoacoustic ultrasound. And lately, we also developed what is called TROPUS. So it's transmission, reflection, optoacoustic ultrasound. So we don't only do pulse echo ultrasound imaging, but since we have full coverage around the mouse, we can do transmission ultrasound, which is actually reconstructing speed of sound and acoustic attenuation in the object, and not just reflection type of contrast. And the results are pretty interesting. So here we image the tumor with both MSOT. So this is the optoacoustic contrast from the tumor. Here you see some vasculature around it. This is reflection ultrasound. And here you see the transmission ultrasound, which is a very different type of contrast because it represents more quantitative values of the speed of sound. And this is now quite hot topic also in detection of breast cancer in humans. Yeah, so this is kind of a multimodal implementation of optoacoustic and transmission reflection ultrasound. Now, if you look at this system, it's quite complicated, right? So it's a very expensive array. You cannot buy it on the market, just on a free market. You have to design it ad hoc. A lot of elements, yeah, so the quite expensive system. So we thought of how can we reduce the price of optoacoustics so to make it really democratize it, I would say. Yeah, so the way to democratize is to reduce number of elements, for example, right? So if you don't have 512 elements, then electronics becomes much cheaper, ultrasound transducer becomes much cheaper, and so forth. Okay, so let's take out some elements. Of course, if you do this, you end up with images like this. So this is the full tomographic coverage image, and then you do every 4th element or every 16th element, and the image is completely destroyed. Okay, but then the whole deep learning hype started. So we thought, okay, let's use deep learning. So we trained it with the images from an expensive system. Used UNet, and then looked at what kind of image quality we get. So we train it with like good quality images, and then we feed this image into the neural network. And actually, it was quite promising. So if you look at undersampled data 4 times, so that already saves you 75% of detectors. It was able to remove most of the limited view artifacts, like undersampling artifacts, and get you almost to the same image quality as the golden standard. In the case of 16 times undersampling, it was not that good, but still much better than. So here you see just noise; you cannot see anything in the mouse. But after the network, you start seeing with maybe a bit lower resolution, but still decent image quality. So that was very encouraging. And we also tried it on a limited view problem. So instead of just taking every 4th element or every 16th element, we just cut out from 360 degrees. So we only detect with 135 degrees or even 60 degrees, like the linear array ultrasound. So why don't we just do it with the linear array now? So with deep learning, maybe we get the same image quality like with a perfect system. Not quite as good, but you can see that with 135 degrees coverage, the image quality is already very decent. And with 60 degrees coverage, this is if you do nothing, and this is with neural network. So again, surface is restored. And the image is much, much better. So it's also useful for doing it in this way. Okay. But, you know, just to a grain of salt. So it's a very useful application, and we saw many more like this. But you have to be careful what you try to use deep learning for, right? So because, I mean, the holy grail of the whole artificial intelligence field is like replace radiologists, for example, right? This is what people are trying to do. So not improve image quality or whatever, but to replace the radiologist. And then you are faced with a completely different scale of problem, right? So it's not just about some reconstruction of optoacoustic images. You know, you really want to replace like human intelligence, and these are the results from a few months ago, right? So I always read these papers and I wonder, like, is it gonna happen ever or not? So so here, like results from a paper in June. So marginal time savings with AI. So 1 second per case saved. Cool. You know, and all of this stuff. So context-specific performance, right? And I mean, you would predict that this would be the case, right? So the problem is just too difficult to solve, right? And there was more optimistic paper published in September, I think, so 2 months ago. Yeah. So this involved 80,000 women, X-ray mammography. So AI helped radiologists to spend 44% less time reading. That's good, right? But then comes this. Effects on the cancer detection rate are questionable. Okay, so So, and this comes like every month, this kind of papers. So, and on top of that, you know, the carbon print, right? So, I mean, come on. Where are you going to get so much energy? Now, I mean, I saw here there's no light on the streets anymore, right? So if you use more and more AI in this way, I mean, the energy is going to run out. So just to train Google Translate, for example, right? So it takes 315 return flights from New York to San Francisco in terms of CO2 generation, right? So this is not really practical way of doing it, right? If you want to, I mean, just think about the carbon print, right? So that's what I always tell people. Yeah, so just use your brain in most cases. So again, not against deep learning, but you have to think about all these problems and choose the right one, not replacing people doing like intellectual jobs. It's not going to happen. I mean, this is like not a problem we need to be solving. I mean, it's just a tool. You know, it's not. It's like another algorithm. That's my view of it. You know. Yeah, and to help it further, you know, a way of looking at intelligence in general is try to mimic human intelligence, right? So not to just do brute force machine intelligence, because human brain doesn't consume so much energy, right? So it's just 12 watt of power, so not 300 transatlantic flights, right? That's all we consume, 12 watts. Yeah, and it can learn very high-level conceptual representations without using any labeled data, so completely unsupervised, right? So how this is done? I mean, this is the question we need to be answering, right? So continual learning, right? So the humans are able to quickly adapt to new situations, right? So not something that machine learning can do at the moment with the current architecture, at least, right? So how biological networks are much more effective in this, you know? And another question is like if you ask, you know, this latent learning. So how this high-level abstract concepts can be learned by humans without use of any rewards or binary supervision signals, you know, without any labels, right? So a kid sees one time a bus, it would immediately learn that it's a bus. You don't have to train the kid with 10 million images of a bus, right? No CO2 wasted, right? Okay, so this is one side of looking at it. Another side of looking at it is physical intelligence versus computational intelligence. So one of the things that children do, you know, they push something and they learn how the object responds immediately, right? Machine intelligence cannot push anything, right? It's just a computer. So that's why it cannot learn, right, so efficiently, because it cannot modify the object or anything. It would be the same, what you show it, this is what it's going to learn. So you need always someone else to, so all this thing about this artificial general intelligence, I mean, if you're not able to modify the object, how this is going to happen on Earth? Yeah, it's not going to happen, right? So the other aspect, if you want to make machine intelligence more intelligent, we need to acquire some physical properties so it can modify things, right? And this is where the field of microrobotics and all of that, like really making it possible for algorithms to sense, to actuate, to control, you know, to adapt to a physical environment. It's super important if you want to take this forward. And this is where we also collaborate with a group of Metin City in Max Planck. They developed this really intelligent acoustically, magnetically actuated robots for different tasks. And one important aspect of it is that once you want to do it in vivo, you want to know where they go in the living body, right? You need to be able to monitor their action on the tissues in terms of therapy or imaging and so forth. So this is what we implemented in this project. So basically, we took magnetically actuated microrobots and reduced them to a size so they can flow freely in the blood, so to a size of about 5 micrometers. Injected them intravenously in a mouse, and we were able to track them after labeling with some gold coating for better optoacoustic detection. We were able to track individual microrobots in the microvasculature in the brain. So here you see these green spots are individual microrobots. So now if you want to see what they do, where they go, you can do it with this approach. Okay, last thing I want to mention, I have to wrap up already, is that so optoacoustic imaging, I've shown you mainly images from mice, but there are many cases where it's already been used in the clinics. Here is a partial list of some cool papers that were published over the last few years on different pilot studies and different indications. I won't go into explaining each one, but maybe just the title. So here is a study published in New England Journal of Medicine to assess Crohn's disease activity, so in intestinal inflammation patients. Another study published 2 years ago on non-invasive detection of metastatic sentinel lymph nodes in melanoma patients. So it's a very difficult clinical problem to actually detect melanin in the lymph nodes, which would tell you that the patient has metastasis. So it's usually done with biopsy. And here they replaced biopsy with non-invasive optoacoustic imaging because it can detect melanin very nicely, right? It's dark, so it really shines on the optoacoustic images. And last example is our ongoing study in Zurich, trying to use optoacoustic MSOT imaging for non-invasive carotid imaging. And here the goal is to detect various levels of carotid plaque vulnerability based on lipid content in the plaques. Okay, to summarize my talk, so what I've shown you today is that optoacoustic imaging is a multi-scale method. So it can take you all the way from microscopy to centimeters of penetration in mice and humans. With tomography, it's safe for human use because it uses non-ionizing radiation. Imaging speeds are really ultra fast and over the last years are getting probably the fastest among all the imaging modalities. It's non-invasive and label-free. If you want to look at certain things like angiogenesis, hemodynamics, oxygenation, lipids. If you want some specific molecular contrast, so genetic or targeted labeling is possible. Sensitivity is quite high. I wouldn't say it's as high as positron emission tomography, for example. So it's not femtomole range, but I would say few picomoles or a few tens of picomoles of contrast agents are detectable in vivo. And then I've shown you also a broad palette of clinical and preclinical application in various diseases. And of course, it's not free of challenges. Again, the field is still growing, and there's a lot of work to do on just the technical usability. So it's too bulky, too expensive still. You know, we could really facilitated imaging depth is a big problem, so it's limited to a few centimeters. So maybe developing some endoscopic approaches to approach deeper tissues in humans would be helpful. Image quantification is a big mess. So there are so many papers coming out with all sorts of different ways of quantify, for example, blood oxygenation. So you do see some changes, but if you want to pinpoint what is the SO2 in each and every voxel, not really possible at the moment, at least not in vivo, to my knowledge. Contrast agents are not dedicated contrast agents are not existing, so almost not existing. We need to develop agents, not take them from other modalities, but develop really optimized contrast agent for optoacoustic imaging. Clinical evidence is very scarce, so just a few pilot studies. And of course, standardization is important, right? So to use it like MRI or ultrasound, this will take quite some time, I would say, to standardize and also get the regulatory approval. Okay, thank you very much.